Dividing square roots. Before we divide, I just want to remind you, dividing works the way you think it would. Adding does not, so don't mix the two up. If I ask you to add root 5 and root 3, you can't do that unless you approximate and make it a decimal. They have to be like terms. If I ask you to add 3 root 5 and 7 root 5, remember that's just like when we have 3x plus 7x. There's no difference. Or even 3 times 10 plus 7 times 10. This I can't do. But the second one there, that's 10 root 5. 3x plus 7x is 10x. And 3 times 10 plus 7 times 10 is 10 times 10. I have 3 here and 7 here. That means I have 10 of them. 10 tens. So adding, I have to have like terms, adding or subtracting. Dividing, you just need to remember, as long as they're both roots, it works just the way you think it would. In other words, root 30 divided by root 3 is root 10. Simple as that. However, I want to point out, for future benefit here, if I ask you to say, do 30 divided by root 3, you can't do that. Now, there's some other things we can do, but remember, root 3 doesn't go into 30. Root 3 is 1 point something. It's a decimal. In fact, it's irrational. It goes forever, and there's never a pattern. It's not going to cancel with 30, a whole number. So you can't cancel unless they're both roots. So if I'm looking for both whole numbers or both roots. So in this next example, root 12 divided by root 2, that is just root 6. As long as they're both square roots, you just divide it out and you got it. And you can check this on the calculator and see that this works. One of the things we run into is roots in the denominator of a fraction, like right here and right here. And in fact, even right here. This, and this is important, you can write this as root 10 over root 14 anytime you feel like it. And remember, as long as they're both roots, you can simplify them. See, both of these are divisible by 2, or root 2. Divide the 10 by 2 and the 14 by 2, and I get root 5 over root 7. This will take some getting used to, but in general, we do not leave a root in the bottom of a fraction. We do what's called rationalizing the denominator. The reason we do this is partially so that we all agree upon the same answer, because it can look a lot different if you don't rationalize. And then sometimes it does simplify the answer and make it a nicer number to work with. But not always. But we will always rationalize whether it simplifies it or not. So if you have a root in your denominator, what you do is you take that denominator, the number in the denominator, and you make a 1 with it. In this case, root 7 over root 7. Only the root part. What I'm going to do is eliminate the root in the denominator. So up top, root 5 times root 7, you've done this, is root 35. They're both roots. I can multiply them. Root 7 times root 7 is root 49. Now I can take the square root of 49. That is a whole number, 7. So my answer is root 35 over 7. Do not try to cancel with the 7 and the 35. Remember, root 35 is a decimal. 7 does not go into root 35, evenly anyway. You could approximate, but the goal here is just to simplify it, write it in simplest radical form. So the only way I could cancel the root 35 is with another root, like root 7, and that's not what I have. This is the answer right here. Root 35 over 7. On this next example, this again brings up the next two examples actually, that you can't leave a root in the denominator of a fraction. So what I'm going to do is take that denominator and make a 1 with it. In this case, it's root 5. So take the denominator, make a 1. Negative 35 times root 5, you can't multiply those. But it's just like when I say 6 times x is 6x. You really can't multiply 6 and x. 6 times x is 6x. It's still 6 times x. You didn't do anything if you multiplied 6 and x. You really can't do it. It's the same thing here. I could multiply them if they are both roots or both whole numbers. So I do just like I did with 6x. I just put them together. Negative 35 root 5, which is still negative 35 times root 5. The denominator, root 5 times root 5, is root 25. The square root of 25 is 5, so this is negative 35 root 5 over 5. Now I can cancel. Because there's times right here, it's like when I say 8 times 3 divided by 3 is 24 divided by 3, which is 8. I can cancel those 3's and I still get 8. The reason that works is because of the multiplication. So the same thing applying here. I have multiplication right there. So the 5 and the 35, they're both whole numbers, will cancel. 5 goes into 35 7 times. So my answer is negative 7 root 5. On this last one, if you can, it's nice to simplify the root before you go and try to rationalize it. Remember the root 50 below, we're not going to leave it there. But I noticed that 50 has a perfect square in it, so you've been doing those. I'm going to take the largest perfect square in 50, which is 25, and rewrite 50 as 25 times 2. I can take the square root of 25, it's 5, so that's 5 root 2. And again, we don't leave a root in the denominator, so we're going to rationalize, make a 1 with that root 2, and I get 15 root 2 over 5 times root 4. Root 2 times root 2 is root 4. So at this point, let's realize a couple things. The 5 and the 15 will cancel. They're both whole numbers, and I have multiplication between my pieces. 5 goes into 15 3 times. So this is 3 root 2 over root 4. But what was the square root of 4? 2. Remember that I can't cancel 2 with root 2. Root 2 is not 2. It's 1 point something. It's a decimal. It will not cancel with a whole number 2. So that is your answer. There's nothing else you can do with it unless you approximate, and that's not what we're doing here. A few more quick examples. I cannot cancel 14 and root 14. The square root of 14 is a decimal. Square root of 14 is 3.741 on to infinity. Those do not cancel. But I don't leave a root in the denominator, so I'll make a 1 with it. 14 times root 14, I can't multiply those. It's just 14 root 14. There's still times between them. Root 14 times root 14 is root 196, but that's a perfect square. And the square root of 196 is 14. So this is 14 root 14 over 14. And because there's times here, just like we did on the previous example, we can cancel the 14s. So there's a 1 in front. You could say 1 root 14. But remember, it's just like when you say 1x is x. I don't need to put the 1 in front. So it's just 1 root 14 or root 14. Next example, when we rationalize here, it really doesn't make the answer any simpler, but it again will make sure that we all agree upon the same answer. Well, we don't leave a root in the denominator, so we'll make a 1 with it. 5 times root 2 is 5 root 2. Root 2 times root 2 is root 4. But the square root of 4 is 2. So 5 root 2 over 2. I cannot cancel the 2 and the root 2. Root 2 is a decimal. They don't cancel. And 5 and 2 are both whole numbers, but they have no factors in common. 5 root 2 over 2. Last one. On the previous slide, we separated the roots. We can do that anytime you feel like it. Root 5/7 is root 5 divided by root 7. And we're going to rationalize. We're going to multiply the top and bottom. Take your denominator. Make a 1 with it. Root 7 over root 7. Anything divided by itself is 1. So I'm multiplying this by 1. It doesn't change the value at all. It just will look different. Root 5 times root 7 is root 35. Down below, root 7 times root 7 is root 49. And the square root of 49 will end up being 7. Root 35 over 7. I can't cancel those. Root 35 is a decimal. 6 times 6 is 36, so it would be 5 point something, 5.8, 5.9 something. And it will not cancel with the 7. I can only cancel a root with a root or a whole number with a whole number.